to today's session. And today's speaker is Dr. Aswad Babu from Department of Physics, IIIT Dharwad. And we know very well he is very fine teacher and expert in quantum information theory, quantum optics, nonlinear dynamics of optical systems, and nonlinear optics. So today he will continue on the topics related to quantum sensing. And yeah, without taking much time, I hand over to the expert today. Aswa sir, please take over. And you can start your lecture as per your plan. Okay, sir.
Thank you, sir. Thank you, Manoj, sir. Thank you very much.
Okay, sir. Thank you.
Yeah, thank you for starting and giving the brief introduction of me. Okay, so dear participants, very good afternoon on the weekend. We'll just wait for a few minutes. At least we will cross 150. We'll start. Yeah, we are going slow as we know this is a weekend. Agreed. So maybe a minute we'll wait and then we'll start. Yeah, what exactly we are going to do today is we are going to talk about the atomic clocks. Okay, so they are actually some kind of a quantum sensors, right? Mm. Apart from this, if we can notice, maybe I'll share the screen. Okay, the other screen it will disturb. Okay, so tomorrow you will have 9 to 11 morning session, 2 to 4 afternoon session. So some other resource persons will be covering the tomorrow's topics, and then I will come back on Monday, 13th of October, and also on the 14th of October. So during then, I would like to cover quantum gravimetry, that is gadiometers, and entangle based sensing applications, and single photon based sensing applications. So basically, it's all about sensing particular sensing devices we'll discuss. Okay, I think We will start. Yes, we have crossed 150. Okay, let me see. Right, so straight away I see a question here by Lakshmi Narasimha Rao ji. If possible, can you please cover the role of quantum sensing in Earth observation systems and remote sensing satellite sensors at any point of QT-07? Applications by any other across the globe. Probably this gravimetry, what I was mentioning, and the one magnetometers are connected to Earth gravimetry and also connected to finding the minerals in the Earth core. Okay, so probably we will touch those things definitely, right? So some part of quantum sensing and quantum technology we are definitely going to touch. Yes. Okay then. So atomic clocks I wanted to discuss for today in the first half. Okay. Right. So as you see, first of all, like any technology or anything, I just want to know what it is. Okay. Right. So first, the first question I would like to ask myself: what is clocks for me? Okay. What is the clocks for me? Right. So clocks is something. Here you see, it will involve two components. We all know that. Okay. So what we do, we just recollect. One component involves a mechanism that oscillates. So we are in the oscillations throughout. Okay, you see how the things are connected. So one oscillations, one mechanism. Another mechanism is that counts the oscillation. Either oscillation is converted into some other counter or some means whatever oscillation created, the information of oscillation is stored in some other form. Okay, right? So the clocks back then, right, involves two components. One is oscillator, the ticks creator in a steady beat. You see, it should be steady, it should not be irregular, right? And the other one is just a count. The most, for most of the history, the oscillating mechanisms have been human made objects. Okay, right? So the swinging pendulum clock, right? And as two pendulums are exactly alike, the time appears to measure may not be exactly same. Remember, humans cannot make it perfect. Okay. However perfect you replicate, even though they appear to be same, they may not be exactly same. One is the environment may disturb them or something may disturb them and they may go slightly out of sync. Out of sync by 1 nanosecond also makes a big difference, right? See how it makes a big difference. I'll tell you one simple, very simple uh, real life example. You make a call to somebody, okay, right? So if there is a 2 seconds delay, right? 2 seconds, not anything more. What happens when we are calling somebody? Whatever voice I sent through my speaker microphone to some other side who is receiving my phone, you see 2 seconds. While I was speaking, he may reply. While he is speaking, I may reply. So there is a overlap of our conversation. What happens? So we'll not able to listen and do a proper conversation. You see how just the overlap of two voices on the conversation at two different points through a phone call gets no sync. when there is a delay in the communication. Okay, so the delay may be happening due to many factors. Okay, so one factor, a technical factor would be, right, whenever I stop my voice at this point, okay, let's say right now the time is 2011, sorry, 211. I stop my conversation at 211. On the other end, sorry, my receiver, the other person who is making conversation with me, he should be able to start the conversation exactly at 211 the moment I stop, or he may take few seconds and respond back to me. Okay, so that we do a one-to-one conversation without any interruption, and we make a meaningful discussion or conversation. This is possible provided our clocks are exactly synced. Okay, the clocks are not synced, right? In that case, what happens? I might tell something like to my friend, I'll call you at 2:15. Initially, the both clocks we started together, both the clocks are same. Due to some problem, my friend, his clock got out of sync with my clock, so it is slightly delayed by 1 minute. Whenever my time is 2:11, if his time is 2:12, so this may cause issue while doing a conversation. This may cause a problem while fixing up the meetings. Okay, so at real world level itself, we are seeing clock synchronization or time synchronization is such a very important thing. But when you go to, let's say, a GPS, okay, so in the case of GPS, right, GPS case, GPS usually uses to locate somebody's location in a on the surface of the earth. Let's say they have a GPS device like a mobile. The satellite picks the location, or the local receiver picks the location and communicates to the satellite. And while the, let's say at some point you are on the ground, let's say you are in a particular location. So the time and location was picked, right? And that same location was communicated to the satellite, and the satellite puts your location on the Google map. Let's say you are in a vehicle, okay, right? So around you these days, Google Maps even give you exact the traffic. How it does? In a real time, it is going to track the location of each individual vehicles. These days, everybody carries the mobile with a GPS. Okay, so by finding the location or by locating someone, it figures out how much traffic is there in a particular road. Okay, it's a dynamic and real time. That means your clock and the clock on the satellite both are synchronized to a very great extent. Even slight change of nanosecond would give you a lot of difference. Okay, so if that nanosecond is there, what happens is the satellite may predict that you are somewhere else, let's say few 100 meters away from your actual location. Okay, it is unable to pick your new location. It might give you as a give you your 100 meter, like few seconds old location as your current location. So that is completely a mismatch in the GPS locating. That is mainly Google Map these days we are using in real world. So that is going to be affected. So the time synchronization is a big deal back then. Okay, so for conducting meetings, for planning anything, the clocks are important. These clocks are human made. Human made things cannot be perfect to 100% extent. So the two human made timepieces can never perfectly in sync, so they drift away from each other. Time wise, I am talking. Drift away from each other by time sense. Okay, very good. Now let's go further. We understood what are the clocks, mechanical clocks. The question is, if I am supposed to have a clock, perfect clock, not a mechanical clock, basically I need to have something which is oscillating, something which is counting. If I go for a larger and larger devices, lot of mechanical entities are involved, lever, spring, okay, those things are involved. Those things will have a wear and tear. Okay, the mechanical things again they have lifetime. Then what happens? These devices go problematic after some time. So for that, what we can do for that is we can go to a tiny scale so that the less wear and tear is there, so that they are exposed less to the environment, and there is less small not big number, like a large number of mechanical entities are involved in it. Okay, so one such a thing is atomic clocks. They are helpful for us in multiple ways. One way is they can sync between, like two clocks can sync in such a way they will go out of sync, let's say very small amount. How small you can't imagine. Okay, right? So that is one way of doing. Another way of doing it, probably they may not be involving a mechanical equipment. So the moment a mechanical equipment is not there, wear and tear is less. Okay, there are other complex things maintaining the atomic clocks. All those things are there anyway. But when it comes to the most important objective, why the clocks were created, you know why the clocks were created? The clocks were created to know the duration, time duration change. At the same time, the sync between multiple people stay apart to do something, to meet somewhere, to do some event together. Okay, so that is the main purpose of clocks. Okay, wait a minute. Yeah, fine. Now here I have atomic clocks could overcome these constraints as they can create almost perfect beats. Okay, the beat mechanism in a mechanical clock, whatever we saw earlier, such a thing is also exist here, may not be exactly mechanical beat. So if I prepare two clocks, I can sync them, they can create almost perfect beats. Okay, number two, since the atoms don't have any manufactured parts, they don't have wear out and slow down over time. Like I said, if I keep using the spring, stretching and compressing, okay, it's made up of some kind of a metal. After some time, what happens? It loses rigidity, loses spring constant or rigidness. So it may not be a spring kind of a thing. Even the elastic materials, okay, with the weather, you know what happens? The elastic actually loses its elasticity, right? This we will observe at home. The elastic material go bad after some time as we start using that. So all atoms of a given type are identical. Okay, why is it possible? Okay, the atoms to start with, more or less, they are identical. You know why they are identical? There will be a nucleus. Inside a nucleus, there are protons, there are neutrons. The number of protons would dictate what is atomic number. and more or less the number of electrons, if I am talking about the neutral atom, the number of electrons in the atom are exactly same as number of protons inside the nucleus. And there are neutrons are there, but they are neutral particle, by the way. They used to club together, keep the, okay, they allow protons and neutrons, right? So inside a neutron, sorry, inside a nucleus, protons are clubbing, neutrons are clubbing protons together, and they help in putting to positive charges and positive charges together, like a neutron. Okay, so you can't have neutron protons come together because they're of opposite charge, sorry, same charge. Okay, so there is a Coulombic force of repulsion exists between two protons. How can I make them to sit together? It is just like after some time, a married couple may have some of the differences. Okay, they don't find much fun in each other sometimes. Okay, what happens if there is a kid between them? Because of the kid, they come together and they enjoy each other's company. Okay, likewise neutrons are like those guys. Okay, now if you see, the main reason is to okay, the main reason is for the atoms is for the atoms to use here as a atomic clock rescuers is they observe and emit waves of specific colors of frequencies, wherein if the light waves turn attuned to these atomic frequencies produces ticks of time that are billions of times more stable and precise than those of any kind of clock. Okay, so talking about the clocks, the clock mechanism in that. Okay, it has to tick, something has to tick left to right, start from left, go to right, and come back to right, left. So it is making one tick. So what such thing if I need to have in the atoms? The best thing is electron absorbing energy in the atom and come to an excited state and go back to the ground state. So if there is a nucleus, there is an electron, there is one more orbit of the electron. Okay, so the separation between the ground state and the excited state, if they say delta E, if I send a photon of energy h mu is equal to delta E, or you can even say close to delta E, what happens? There is a chance electron can be shifted from, I'm sorry, I'm getting ground to excited. Okay, now if you see, so electrons cannot stay in excited state forever, we know that they can only stay for 1 microsecond, right? So after 1 microsecond, what happens? The electron just drops back to the ground state and they just emit whatever energy they observe as the same amount of photon. There is no change in the photon energy here. Interesting. Okay, now that is a absorption emission. Okay, so there are two ways of emission I can have. One is spontaneous emission, spontaneous emission in atoms. Okay, what is that is, by the way, somebody has given an energy to the electron, okay, in an atom, so it is exist in the excited state. Okay, what happens after 1 microsecond? It drops back and emits that radiation spontaneously. Okay, there is nobody is telling, it just emits spontaneously on its own. It's called spontaneous emission. Okay, but let's say the electron is there already in the excited state. Okay, right? If I let it to decay to ground and see the emission of the photon, I am not having that much time. I want to put the electron to the ground state and get the photon out even before what I was waiting for. So in that case, what should I do? I have to induce the emission. I have to induce electron to come down to the ground state by force. Okay, we are all doing these things using photons. So photons are the ones which would help me again to do that forced emission of the atoms. Okay, so again this time also I will send a photon having energy exactly equal to the separation between the two levels, which is ground and excited. This time usually what our thought is, when I send a photon, if the electron is in the ground state, I assume that it might excite or it may not excite. But there is other way around also, one more option. What is that option is, if I excite the electron, sorry, if I have a electron already excited, if I send a photon, this time what happens, So this is what usually we say, right? If somebody is very good studying, minds with their own business, the guy who is a rogue, okay, right, don't bother about the career, and he will come in his company. What happens? The good guy also becomes bad. Or you can think in the other way, right? What you can think in the other way is, okay, a bad guy is there, a good guy comes and spreads his goodness to the bad guy. Likewise, here the photon which is coming sees the electron in the excited state, somehow triggers even before its lifetime, it triggers the electron to come down, and whatever energy with which it is excited, that much energy is emitted along with the traveling photon. So let's say the traveling photon is of h mu energy, and electron which is already of excited state of h mu, that also came down and emitted a photon of h mu. Here you see I have one photon and I obtained two photons by doing the stimulated emission. The beauty of this one is I can induce the direction or some kind of a property relation between the probing photon, or it is also called a pump or probe field, okay, and the one which is coming from stimulated emission, let's say this one. So there can be a relation between these two by choosing the way I take the material and the way the cavity setup. I can ensure that. Okay, so this is a stimulated emission for you. So when I want to de-excite an electron from ground to excited to ground, I can do it in two ways. One is waiting until it does on its own. Another one is I forcefully put that to ground. Okay, so using this mechanism, people started creating uh, ticks around vibrations or oscillations. How? We already seen this kind of a mechanism, something like putting the electron from ground to excited by sending one photon. So electron goes and comes down after 1 second, sorry, 1 microsecond. So with 1 microsecond apart, you place one more photon, another photon. You basically you are going to keep a sequence of photons separated by 1 microsecond. If they have to be represented in the form of pulse, it is a nice single peak, nice peak pulse. It is a pi by 2 area of the pulse. Okay, right? So pi by 2 area pulse, which comes and interacts with the atom, puts the atom in the superposition of ground and excited continuously. Okay, fine. Okay then. So let's get back to the presentation. Yeah, here you see the atomic transaction frequencies offer a best, purest, most stable beats in the universe. So they're saying whatever beats we are getting oscillations, they are the perfect beats to measure the time. Okay, so 1 second is actually equal to certain number of beats. Okay, so I can tell somebody my 1 second unit is this device, this atom device does the oscillations ground to excited, let's say some 9999 times. So the other guy has to also use the same unit to represent his time duration of a particular thing. Okay, right. So talking about the purest system, whatever we have here, and best system, atom system as a clock. So there is a question here, Veeramanikyam ji. What is the role of pure and mixed state here in the context? Atoms stimulated emissions and along the oscillations, which is exactly observed and excited as you said. Okay. So when I say a single atom for excitation, I may not be referring to exactly single atom. I'm referring to multiple atoms. But multiple atoms, not all are having same kind of environment. The ones which are, let's say, remote, ones which are there at the very edge, their surroundings may not be same as the ones which are at the center. Because of that, what happens? I can't read them all in the same way. Here also, so I have going to have a mixture of a combination of atoms of one kind, another kind, another kind. Okay, right? So this is what you please understand. Okay, very good. Now let's go further. The pure and mixed state comes wherever we do quantum computing, wherever we are going to take a collection of atoms or qubits to do the computation, where not all are same. So I'll have a mixture of systems, and that it will be a mixed quantum system represented by density matrix rho. So density matrix rho would help me to tackle the actual scenario of computing by taking the notion of mixedness in the chosen resource of qubits. Okay, now let me go further. Okay, and one more thing, we were talking from earlier, and it's part of our QT also, QT-07. The resonance is a very important part of anything. Okay, so why I am saying about resonance is, here I have at the right side there is a diagram. A kid is playing in the swing. Okay, now if you see kid, if it swings on its own, it somehow it figures it out when to give a jerk of going up and down. Let's say if the kid is like, the parent is there, is pushing the swing, standing at some point. Okay, and at one side he or she will stand, pushes the swing along with the kid. By the time it comes to him or her, by the time it is about to leave, that time it pushes, so that the swing, the motion of the swing as well as your push, both are in same direction. So basically, unknowingly you are actually putting your force in sync, in resonance with the motion of the swing. Okay, now the diagram which I was showing earlier, the placing of photons must be in sync, the energy with which I am giving in sync. In the same way, so each individual photons must be in sync in time domain, they must be placed. Okay, so that means the system must be in sync with the incoming energy. I can say in the other way around. Okay, so how can I ensure that? One thing is, I can't give a something inappropriate force in the swing. I have to exactly guess and figure it out. What would be the minimal push required to make the swing to a greater oscillations, right? If you notice, if you play to the swing in the park, if you notice, the amount of push you are giving is not much. Okay, if you want to move such an object from still position to moving position, you have to put a lot of force. But when it is swinging, that time you are just giving a slight tap. Okay, so that tap is enough. That is what the resonance is. So here, what I was talking is, we cannot use just any light, but we need to use a light that has been finely tuned with the special frequency known as atom resonance frequency. So the delta E and h mu must be exactly same. Okay, so when the light frequency is near to this resonances, right, to this transition frequencies, the atom can absorb some of the light's energy, as the electrons could make a transitions, okay, often called quantum jump. Why it is called a jump? See, when we jump, we will not travel through the space. We will just move from that one location to other location by hopping. Okay, so even in the case of electrons can't travel from the ground to excited as if somebody is walking. It can't do that. There is nothing exists in between ground to excited. You know why? I'll tell you what. So if you have ground and excited like this, 0 and 1, so electron is here. To go to excited state, it needs an energy. So what it is actually is what you do, you just take this figure and tilt it. When you tilt, what you see, the figure is appears to be like this. This is ground, this is excited. So electron is here. So to go from here to here, basically what it has to do, it has to climb a hill. Okay, the hill of energy. Okay, it has to climb the hill of energy, right? And it has to go to the next level. How it is possible? Only some photon comes and use that energy to climb and go to the other side. But in quantum mechanics or in quantum systems or quantum domain, the electrons would just disappear and then simply go and appear on the other side if sufficient energy is provided. So that is called a quantum jump. Okay, simple quantum jump. Okay, so right, a simple example revealing the magic of resonance would be a swing in a playground. Okay, that we just discussed, right? If on the other hand, if you push the random intervals, push at the random intervals to the swing, it won't go higher and might even come to rest or stop. That is what I'm saying. If you go and sync in out of resonance, you are going to disturb the the disturb the actual oscillations. So there is a possibility to have a resonant frequency for the atoms. There is a possibility to have resonant oscillations in the atom, and that could be used for having atomic clocks. Okay, thumb ticker and counting mechanism, right? So let me see. There is a one more question here. Atomic clocks or clock beats important for tomography. Okay, in order to reconstruct or sensing data from sensors. You name any application which needs a proper timekeeping. Okay, any application is here. There, atomic clocks could be a very handy tools. Okay, for example, you asked your friend to come for a meeting at some location. It's a 5 o'clock in the evening, right? So if a friend comes 5 minutes early or 5 minutes late, it is not going to make a big difference. Okay, but on the other hand, if your flight is, let's say, at 5:30, okay, so the airlines usually ask at least 45 minutes before. You have to be there at the gate to just board, okay, because boarding stops before 45 minutes, right? So by any means, your timekeeping with the airline time, if it is offset by, let's say, 5 minutes, okay, what you do, instead of coming before 45 minutes, you come just before 40 minutes. Because of that, what happens, you might lose a chance to board the flight. So you have to do through hustle of requesting and repeated requesting, and if the airlines are kind, they may allow. Okay, so that is the story. Yeah? Now if you see, right, okay, that's the answer for your question. Everywhere the atomic clocks can come handy. Okay, now what ticks in atomic clocks that allows counting time? This is a basic question you can ask, right? As we tune the light frequency towards the atom's resonant frequency, more and more atoms will absorb from the light and make quantum jump. Like somebody was asking earlier, I think Lakshmaranji asking, what is the mixedness and a pureness here? Sorry, Veeramanikyam ji. So, like I was talking, many atoms we are talking and bringing into this picture of atomic clocks. So, I am sending a light. Okay, many will absorb the light energy. Right now, by measuring how many atoms have absorbed energy, we can detect when the light, okay, light frequency has reached the resonance frequency. So the question is, okay, so in the park, you would know unknowingly without knowing any physics or science or mathematics how much force to be given to give a push. So this happens by some practice, repeated times. Probably first 2 times or second time, you might fiddle with in a wrong way the pushing the swing, but later on your biological the like muscle memory will pick up when to actually push it. Okay, so when it comes to atomic clocks, I can't talk in terms of a single qubit by creating a qubit. Okay, but I need to worry about some other way. How? They take a bunch of atoms, they send the stream of light with the photons having frequency and energy of photon matching the transition frequency of all these atoms. Now, at a given point, what I will do, I'll count the number of atoms have absorbed the energy. If it is in resonance, the light incoming light, the absorption would happen. Okay, so what we will do, we will count the time in terms of counting the crust and troughs of the resonant light, which would be converted to the number of ticks of the time. Okay, the resonant frequency, crust and trough. Okay, so maximum and zeros. You see, this is crust and this is trough. Okay, right? How many photons have absorbed the energy allows us to detect when the light frequency has reached the resonant frequency. There is a certain threshold, then we will decide the light is in the threshold frequency, sorry, in resonance frequency, and then we will count in terms of the crust and troughs of the resonant light, which is matching with the oscillating system. Now, when it is in sync, it might emit the photons also in the sync by doing the oscillations electrons. Okay, so I just put everything in the sync, the incoming light, oscillations, and the emitted light. So from there, I will just figure out how to count the duration. Now the question is, how many cycles of crust and trough do we need to to count one of the tick of a second? Okay, so we'll be counting, okay, between some time, how many times of maximum I just got, that is a crust. How many times of zeros I got, troughs. Okay, within certain duration time, let's say in 1 second, how many I am getting in a given light. So that is how we are going to create a counting the ticks. Okay, the crust and trough of a wave I'm talking about. Okay, so usually it is understood much easier in longitudinal waves, not in a transverse waves. Longitudinal waves are something like, okay, if you have a sling, I think you might know the sling, sorry, not a swing. Okay, so what I'll have, okay, so here you see the spring is elongated, here it is compressed, elongated, and then compressed. So this is a longitudinal wave. So the crust and trough, okay, let me call this as a trough, crust and trough. Okay, see, between each trough there is a crust, so I can count that. Now let's get back. How I am going to use atoms for that job. Okay, so what is that atoms people are being using is the cesium atoms, and whatever clocks they are coming up is called cesium atomic clocks. So what is this clocks so special is, as the atom frequencies associated with this cesium electronic transitions, okay, are so reproducible that the definition of 1 second is now tied to the frequency associated with this transition in cesium 133, atomic number 133. Okay, now if you see, I can have a cesium here atom with me. I can count how many number of oscillations the cesium atom will do when I send a resonant light source towards it. And if somebody is in, let's say, Europe, they will have a cesium. They do the same experiment. The number of oscillations it make in 1 second is absolutely same. So it is reproducible. Unlike a mechanical clocks, even made by humans, it can't be perfectly synced. But the cesium based ones are perfectly synced. It makes 9192631770 cycles of standard cesium 133 transitions in 1 second. See how many? So the other person also makes this same number. So I can have a clock designed based on the cesium atoms. Okay. Now, what is so special about this cesium? Why not some other atom in a periodic table? Okay, element in a periodic table. We'll just see this. Okay, the current time standard for the United States in cesium atomic frequency standard, and which is at the, like a clock made up of this, is at the National Institute of Standards and Technology in Boulder, Colorado. And this is mechanism and this way of counting time or timekeeping started in 1967 as to define a standardness of 1 second as a unit of time. Okay, So they said if cesium atom makes 9 into 10 to the power of 9 oscillations, then whatever time it took to make these oscillations, you can term this as 1 second. Okay, right? And I can convey the same information to somebody in Europe. They will do the same, and we will have two clocks synced together while starting. Let's say two clocks are switched on, and now since in a given second this is not going to vary any number irrespective of the surroundings or anything, what happens, you just start the clocks by in sync, and if you take it apart with different places, but still they're in the sync. Okay, so that is why these cesium based clocks were used. Okay, so that is in 1967. Just prior to that, if you see 1964, the international standard second has been based upon orbital period of the earth. Okay, so people who are sticking to the fundamentals. Okay, but compared to this orbital period of earth, the cesium clock period was found to be much more stable than Earth's orbit. The SI unit of a time, the second, is now defined by this transition in cesium. You are saying probably Earth is slightly going close to Earth. It is changing actually its radius also. Because of that, what happens? Because of that, what happens? We are going out of sync if there is any two clocks were at two different points. Okay. So here I have the cesium clock has demonstrated a stability of very important 2 parts in 10 to the power of 14. Okay, so if there is any error would happen or unsyncing of two cesium clocks separated at some distance would happen, they may deviate from each other by 1 second in 1 into 10 to the power of 6 years. Okay, so very large amount of time. But still, okay, when it comes to highly sensitive timekeeping synchronization, in that case, even this is not sufficient. Okay, so when this is not sufficient, people always start looking for other technology where they can have a better synchronization and better timekeeping. Okay, right? So little will go a little bit more into the details of what is the cesium clock. Okay, what is a cesium atom? Okay, all right. So there is a question I will just take, and we'll take a break right now. Quantum jumps with a resonant frequency in the qubits, more with the qubits similarity and any possibility of entangled state as well as the multiple qubits. I understand your question. Okay, let's say a cesium clocks are there, you created out of atoms. Can you have some entanglement to enhance the synchronization? Of course, it's a very good idea. People are already thinking about, right? So two entangled atoms may have a better synchronization. If something happens here, something happens there immediately, even without any time. Okay, entanglement is the main implication there. Okay, right? So yes, adding entanglement is going to add a new effect, an additional effect. So yeah, it's possible. Fine. So now its time is 2:55. We'll take a 5 minutes quick break and then come back at 3 o'clock, and we'll finish off this atomic clocks, and we'll touch little bit of for the Monday session some Raman spectroscopy, which is required to be understood little bit more in detail. That we will touch for today. Okay, right? So we'll take a break.